Good morning, everybody. So, do you have any question? Okay, just to follow up from yesterday, I saw the book, Aditi, your doubt. So I looked in the book how they have done it. Okay, so it is actually similar to what we discussed yesterday. Only thing is, just taken a special case basically. So final form that we get while converting from uh, the weak formulation to a strong formulation, it looks like something like this. WL multiplied by F naught minus EA du over dx at x equal to L, right? Plus uh, we have taken something like this, phi x, and then we have d by dx EA du over dx, right? Plus bx, a square of it, dx, right? That is equal to 0. So in book, this WL, we know that W0 has to be equal to 0. However, this WL, we don't know what it is, right? So you can, since this is valued for all W, hence you can also assume that WL is 0. You choose as an example, because if something is, it has to work for even for one example. Even for one example, it has to work. So you can choose WL equal to 0, choose an example. Yeah, and in that case, what happens? This term will go, only this will remain. So example of that will be, for example, if you have phi x equal to x multiplied by x minus L, for example, right? So automatically at x equal to 0, phi x will be 0. At x equal to L, this will be 0. And since this is here, automatically the W being equal to phi x multiplied by d over dx, EA du over dx itself, automatically WL will be 0, W0 will be 0. So both will be 0. So since this has to hold true even for one example, and that really means it's only possible, it will hold true only when this whole thing is equal to 0, and hence this will be 0, right? So that really means that tells that 0 to L Wx, not Wx, phi x, and d over dx EA du over dx plus bx square dx has to be equal to 0, right? And hence it follows this has to be 0. The other one, if this is equal to 0, that really means that WL times F naught minus df EA du over dx x equal to L has to equal to 0, right? Okay, if this is equal to 0, in one example you have taken WL equal to 0, you can take another example, right? Because that has to be true in other all examples, right? So another example will be is also valid. And you can choose any, right?
So your voice is breaking.
You guys are with me?
Yes, sir.
Yes, sir.
Keep my camera off. Okay, maybe because of the bandwidth, it creates problem. Okay, so did you get it? What are we discussing?
Yes, sir. Yes, sir.
Yeah. Okay. Okay. Any other question, guys? Since you have quiz on Monday, so any other? Okay. If not, so we will move ahead. So now we will take up the original problem that we have discussed many times. Again, I'm saying that I'm taking simple examples because it's easy to understand. However, they are powerful. If you see that there was a question yesterday that why do we have to convert into weak formulation? So we are looking at very simple problems. That's why you think that it's not required. But if when you go to something which is not some problem, diffusion problem, for example, or a heat transfer problem, in that case, you will have no idea unless you convert into weak formulation. That makes life easy. Also, instead of 1D, if you have 2D problem, plane stress problem, in that case, it will not be easy unless you convert into the weak formulation. So this is one example of problem being complicated. So simple thing is, if problem becomes complicated, then unless you have some mathematical basis, you will not be able to find out what to do. Yeah, so that's why we do. And hence we will see, as it progresses, you will see that this course is like that only. It starts with very simple problem, the 1D problem, then goes into 2D problem. You can extend it to 3D problem, and so on. So this is what we will be doing. Okay. So anyway, so this is a problem that we have discussed earlier. This is again 1D elasticity problem, and the problem is EA du over dx, right, plus bx, this u, is equal to 0. Okay, and boundary condition, u at 0 equal to 0, and EA du over dx, x equal to L is also equal to 0 because there is no force here, but it has body force. So we have that, and we solved earlier. You can solve it directly from here, right? So also, Vx is a constant called V naught. If that is somehow it is I'm writing here, but it's not coming. You guys are with me? Can you hear?
Yes, sir.
Okay, so we have this problem d over dx ea du over dx plus bx equal to 0, and bx is constant. Yeah, and we you can solve the problem d over dx, and then you have ea du over dx plus b naught is equal to 0. Or finally, if you solve it with the boundary condition, you will get, we have seen that ux equal to b naught over ea, and then you have b naught l minus b naught lx minus b naught, oh sorry, b naught is already there, so lx minus, so let me, lx minus x square over 2. So if you put L here, so then it becomes, that really means some U0 is equal to 0, UL is equal to, put L here, L square. So that makes it B naught L square over 2EA. Yeah. And similarly, you can find out U at L over 2 is equal to, here becomes L over 2. So L square over 2 minus L square over 8. So what do you get? Half minus 8. So 8 and 4 minus 1, right? So 3 over 8. So you get a 3 over 8 B naught L square. Yeah. Then you have, yeah, B naught L square over EA. Right? Okay. So we got these three values. Really sorry, guys. So we have u at x equal to 0, u at L, this value, u at L over 2, we have that value. So so these are the exact solution that we know. Now we will compare the solution with respect to different kind of arrangement. And let's say the same problem, we want to solve it as, this is B naught, right? So we want to now solve as two noded. So one node here, node number 1, node number 2. And we want to, three scenario we want to take, okay? So first scenario will be single one noded, sorry, two noded element means one element but two noded elements. Number two is we will take two noded elements, and number three you will take one or single one three noded element, and we want to compare with what we have at number 0 exact solution. Yeah, so we want to compare the results that we get with the exact solution, and that's what we will do. Okay, so today we will do a few, maybe a couple of them, or maybe if possible we can even do the third one, and if not, then we will continue in the next class. Now single two noded element, so we have this situation, right? And we have node number 1, node number 2. Yeah, and what do you do? If you see, we have to look at now, because B0 is there. So again, any problem you start with actually weak formulation. Okay, so after some time you will know basically where you need to go to weak formulation, you know. So we don't know right now because B0 is there. So our equation is right now our equation, as you know, is d over dx. E and A are constant, so we can have EA here, d over ds square dx squared, this plus B0 is equal to 0, right? So where B0 is a constant. So this is the equation we have. When you say weak formulation, let's do once because this is applicable to all of them. So multiplied by W and EA ds square U dx square plus B0 dx 0 to L is equal to 0. If that is the case, finally what we will get? You get EA W EA du over dx, and then you have L0 minus 0 to L EA dw over dx du over dx plus 0 to L B naught W dx equal to 0. This term, you see, it is appearing. We have to take care of that. Now again, what we do is Wx is equal to maybe Ux first. Ux equal to U1, okay, N1 plus U2 N2, and similarly Wx equal to W1 N1 plus W2 N2. Yeah, and that means we put these values now here. Now remember that if you put WL, the value of du over dx at L is equal to 0. So this will cancel for when x equal to L. Here W0 will come, W0 will be 0 because U0 is 0. So this term will not be there. So only we have is our final equation is 0 to L EA dw over dx du over dx is equal to 0 to L B naught W dx. B naught is there here, right? So actually this whole term will be K times U. This term will give you F. That's the deal. Yeah, so automatically the first term will be coming here, but we want to see how exactly it is working. Now we will put the value of U and W. So we get 0 to L you can take EA outside because they are constant. Then we have d over dx, and then we have u1 n1 plus u2 n2, right? So then this is u, then we have w also d over dx, w1 n1 plus w2 n2, then dx is equal to 0 to L. Then we have W, right, here. So W1 N1 plus W2 N2 multiplied by B naught. B naught is constant, so we can have B naught outside dx. Or you can simplify and you will get equation will be like this. Equation will be W1, W2 like this. And then we have K here. And then we have U1 and U2 is equal to, we will have W1, W2, and we will have F1 and F2. Yeah, of course, this we know already, where Kij, we can write like this, where K is equal to K11, K12, K21, K22. We will find out what the value is. And we have F1. See here, this is our W1, W2, so W1, W2. And then we calling it that. So we can find out what exactly that is. This we have simplified earlier also. We have done earlier also. So K, where Kij is equal to 0 to L d EA, right? EA dni over dx dnj over dx dx. So this we have worked earlier also. The same thing has appeared here. Yeah, it is the same thing. Yeah. Only thing is this term we did not see earlier because we took some other example. Now we have the B naught term here. So we have this one. So see here, this is W1 times N1 plus W2 N2. So
Sir, your voice is breaking.
Ni. Yeah, okay. Is it okay now?
Yes, sir.
So we have N Fi is equal to B naught Ni, yeah, multiplied by dx. That's it. So you can see from here, this is F1. See here, this multiplied W1 multiplied by F1. So this whole thing is equal to W1 times F1 plus W2 times F2. So whatever multiplies by F1, W1 is F1. So what multiplies by W1 is F1, means B naught multiplied by this Ni. So B naught integration N1 dx must be F1, right? So we get the force based on the body force, right? So Fi is equal to this. Very simple. If B are not constant, in general, you can write Fi is equal to 0 to L Bx Nix dx. So it will appear like that. If B is a function of x, this time it was constant, so it came out. Otherwise, it will be inside only. So automatically gives you the expression for the force. You did not have to do anything. Yeah, it's so powerful. Yeah. So accordingly, now calculation. This we have done already, right? Where Ni x is equal to, as you know, x over L, and N, this is N not I was N1, this N2 x equal to x over L. And if you put these values here, you will already, you will get this, you can do yourself, you will get the same value. So K we got here. Now what about F? F1 and F2 we have to calculate. So F1 is equal to 0 to L B naught, and N1 is 1 minus x over L dx. Okay, so B naught, and then we have x minus x square over 2L, L over 0. You put the values, so you get simply B naught L minus, and you have L square over 2L, so L over 2. So L over 2, so you get B naught L over 2. Similarly, F2, you get B naught 0 to L x over L, because this is N1, right? So N2 is equal to, so this B naught, then you get L x square L to 0, and you get simply this also B naught L, sorry, this x square over 2. Yeah, so B naught L over 2. So you got F1, you got F2, both of them. Yeah, and then that means our Ku equal to F, where K is equal to, we calculated EA, EA over L, 1 minus 1 minus 1, 1, right? And U is equal to U1 and U2, and then F is equal to, we got B naught over L, B naught over L over 2 transpose of that, right? So our equation is E over L, 1 minus 1 minus 1, 1, U1, U2 is equal to B naught L over 2, right? 1, 1. This is the equation. Only thing is, what is the problem here? We got the equation. However, you have to apply the boundary condition now, right? Boundary condition is not applied yet. U1 you are writing, but if you invert, what happens? Can you invert it? So if you want U1 and U2, then it will be L over E. One, one, two, So I was asking, is it possible to invert this one? Anybody?
No, sir. No, sir.
Not invert because it's 0, right? So that means there is some problem. Okay, so determinant is 0. It's you cannot get it. That really means that it has infinite solutions. Yeah. So K is not invertible. That really tells you that K has some dependency, right? The two rows will be the same. That really means two rows, two columns are same. So they are dependent on each other. That is infinite solution. Infinite solution of U1 and U2. Yeah. And hence you are not able to do it. But you know that in that problem, U0 is equal to 0. That really means U1 equal to 0, right? So now you can put that value. So here the initial equation, E over L, 1 minus 1 minus 1, 1, and then you have 0, then U2 is equal to Yeah, and B naught L over 2, 1, 1. Yeah, so you have this 0 value here. That means you don't take this row, don't take that column, so you have just U2, so EA over L times U2 equal to B naught L over 2, right? So that means EA over L times U2 equal to B naught L over 2. And that tells you U2 equal to B naught L square over 2EA. Right? So that means what? This is the U2 you got. That is U2 is what? U2 is nothing but U at L. You get B naught L square over 2EA. And you know that it's a linear solution. So far, if you see your solution, so this is X, this is UX, and your solution, exact solution, goes like something like this. Yeah, so you have right. So this one is L, this is 0, and this is exact solution. And your solution right now, the one you got, is like this. Yeah, this this value is B naught L square over 2EA. So 2 noded, so this is matching, but in between it's not matching. Yeah, so this is the solution you got. Now, so far so good, guys. Any question? Okay. Now, next thing is if you take two of them now, right? So what you're going to do is you have this element, 2 elements. So this is element number 1, element number 2. You have from here L over 2, L over 2, right? Okay. So what happens? You can now write directly. Yeah. So you don't. So you take one element at a time. Length is L over 2, and it has EA, right? And here N1 and N2 will be what? Equal to, so this L over 2. So basically, in this case, N1 will be 1 minus X over L over 2, and N2 will be X over L over 2. So it will be 1 minus 2X over L. This will be X 2X over L. You can either do like this, or you can assume L naught equal to L over 2, and then you formulate like that. L will be equal to 1 minus X over L naught, N2 equal to X over L naught, and hence you do all the things like earlier. K for the first element will be EA over L naught, 1 minus 1 minus 1 1, but you know L naught is equal to L over 2, right? L naught L over 2, so you can put that value here. So that will be 2EA over L, and 1 minus 1 minus 1 1. Mathematically also you can get exactly the same value, and since here there is no difference between this and this, both elements are same, right? So you can copy it directly. Yeah, so no need to calculate again. So say Ka2 is equal to 2EA over L, 1 minus 1 minus 1 1. So you can also mathematically you can prove that both are, you will get the same value for both of them, right? So for both the elements, you got that K, right? So you can assemble that. So big K is equal to 2EA over L, and you have 1 minus 1 minus 1 1 plus 1 minus 1 minus 1 1, and rest is 0 here. Yeah, so equal to 2EA over L, and then 1, maybe not write it here. So final will be 2EA over L, 1 minus 1 0, minus 1 2, minus 1 0, minus 1 1. Okay, now what about the force? Okay, so we have to see. Now take element number 1, and you have this B naught, and you have length L naught, right? So for element number 1, the force vector, let's say call F1, right? F1, this is the force vector, will be equal to F11 and F12. This is element number, this is the first node, second node. Yeah, where F11 is equal to, as we did earlier, right? So B naught 0 to L N1 x dx, which will equal to, this is L naught, right? We are putting L naught. Yeah. Okay, and that really means this will be B naught, and finally, similar to earlier case, right? It has a similar expression, everything. Instead of L, we have L naught, that's it. So we get B naught L naught over 2 simply. Yeah, and similarly, F12 is equal to the same value, it will have B naught L naught over 2, but L naught equal to L over 2. So this will be B L over 4. Similarly, this will be B L over 4. Right? Yeah, similarly for element number 2, what do you get? You get F21 is equal to, now here, instead of X, you may, since this is a second element, right? This is a second element. This is exactly same actually. The B naught is not depending on X. N1 expression, you can write the same way only. And in local coordinate system, let us say from here your zeta starts. So you can write L naught B naught N1 zeta d zeta. I'm writing zeta here so that not to confuse with X, because your X start here. Yeah, this is a second element. So here there is a coordinate system should start from here, right? So let's say that's a zeta, and in terms of zeta, you can frame your interpolation function as I explained yesterday, right? So this is like this one. Now explain I was saying that here expression of shape function is similar to earlier, and this is element number 2, for which we have a zeta coordinate system starting with first node has the origin, so we can write in terms of zeta. We have zeta system here, and this expression is same as earlier only. So here also, if you do integration, you will find F21 and F22 both will become at B naught L naught over 2, but L naught is equal to L over 2. That really means that value will be B naught L over 4 as earlier, right? Okay, so now what will be the equation? The F will be, in that case, we have two equations. I mean, And what equations we have? We have the K1 U1 is equal to F1 and K2 U2 is equal to F2. Yeah, so we have EA to EA over L, 1 minus 1 minus 1, 1, and U1 U2 is equal to B naught L over 4, 1, 1. This comes from the first one, and this is from the first one, and this is similarly you will have EA over L, 1 minus 1 minus 1, 1, U2 and U3 is B 4. This comes from number 2. So now if you find it together, automatically this will be a symbol and this will be a symbol. You can one, you yes, you should be able to write in terms of one you can combine them. Sorry guys, the internet connection is really very bad. So if you combine them together, then what you will get is 1 minus 1 0, minus 1 2, minus 1, then 0, minus 1 1. Yeah, and then you get U1 U2 U3 is equal to V naught over L over 4. You will get 1 2 1. Right? So or simply you can, what you will do is, since this relates to this row relates to degree of freedom 2, this is for 2, so you can add them together, so that's what becomes 2. Yeah, and here also this will be this and this will start here, so that's why this is added here. So you know the already in chapter 2, that's why chapter 2 is beneficial. So we have that, and the rest is you apply the boundary condition, you solve the problem. So you have 2EA over L, 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1, and you have U1 equal to 0, then U2 and U3 we have to find out equal to B naught L over 4, then 1 to 1, right, like that. You know that 0 here, so this and this you will ignore, so finally we have this value U1 U2 and U3. So U2 and U3 will be equal to L over 2EA. So we have inverted that already. Yeah, then we can also multiply this, multiply B naught L over 4 multiplied by, we are going to invert 2 minus 1 minus 1 1, then multiply by 1. So this. So this should be U2 and U3. This is equal to L. So here we get this L square. Okay, B naught divided by 8EA, right? So B naught L square over 8EA, and then we are going to invert it. Yeah, and we get 1 and 2, then 1 and 1 multiplied by 2, 1. Yeah, and is equal to B naught L square over 8EA, and then we have this multiplied with this, so we get 3 here. So 3, and here we have this multiplied by this, so 2 plus 2, 4. We get 4, right? Or what we get? We get that really means that U2 is equal to UL over 2 is equal to 3 by 8 B naught L square over 8 EA, and UL is equal to 4 here, so half, right? So we get UL over 2 equal to U2 equal to 3 by 8 B naught L square over EA, and UL is equal to U3 is equal to half B naught L square over EA. Right, so this, if you compare with our original solution, so far, what do we have? You have this we have X here, you have UX, and when the actual solution is, okay, maybe like this is the actual solution, how it is actual. Then you have this one, which is one noded, one two noded element. Okay, number 3, what we get here, you see. Yeah, so this is L over 2, this is L 0, this is L. Yeah, and we get like this. This is matching exactly. You can see we actually saw this value 3 over 8 B naught L square over EA. The same value we are getting here. Yeah. So see here, single element matches at first node, both the nodes at x equal to 0 and x equal to L. But if you take 2 nodes, it also matches here automatically, right? So this solution, 2 element solution is better than 1 element solution. If you increase the number of nodes, this is going to closely follow the exact solution, and hence we do refinement. Yeah, mesh refinement. When you say, then length of the element you reduce, and accordingly that. Yeah, so if you want to make even better, you know that the solution is quadratic, and somehow if your interpolation function is quadratic, then you could have got this function, this U exactly. And for that, we need to have an element which is quadratic, and it is possible when only when we have three noded element. Three noded element will have a quadratic shape functions. Yeah, and hence if you use three noded element, you can find a solution which is exactly as the actual solution for the example. Yeah, so that's what we will do next. Yeah, so any questions, guys?
Sir, could you repeat this last statement about three noded element you said?
Yeah, so three noded element is a quadratic interpolation function it has, and because of that, the solution you find will be the same as the actual solution. That's what I said, and that's what we will do next. Okay, next week. Fine, guys.
Okay, sir.
Yeah. So next week on Wednesday we will have regular class. Okay, so let me finish a few things. After that we will do, I don't know, on Thursday or Friday we will do the tutorial. Okay, so but on Wednesday it is supposed to be tutorial, but chapter 4. Yeah, so maybe we'll do tutorial on Friday or something. Yeah. Okay, any question, guys? Sorry about the internet connection, guys. It was not good, but yeah, so any question?
Sir,
Yeah.
sir, can we solve one problem from the book, from the chapter that we are doing?
Which problem?
Sir, any one of the 3.11 or 3.13, because these are not like these kind of problems are a bit different and not discussed.
Just hold on. Let me see. Okay.
Okay. Yes, sir.
You are saying 3.11 and 12, right?
3.11 or 12, any one of them.
Okay. 3.11 or
Actually, like, so these are like differential equations given to us and a bit different.
yeah. Find the weak form for the following a strong form.
Yeah, yes, sir.
Yeah. So okay. So let us say 3.11 you are saying, right?
Yes, sir. Yes, sir.
Okay. Yeah. So let's look at that. So the strong form, which is given to be k d square u dx square minus lambda u plus 2x square equal to 0. Yeah, and it says that this kappa and lambda are constants, and x varies from 0 to 1. Yeah, and subject to u0 equal to 1 and u1 is equal to -2. Now you tell me what difficulty are you facing? What exactly, I mean, how were you not able to solve this? You tell me first.
Sir, actually, I was, I mean, solve it, go with it, but not get the like what we are regularly getting in our solutions in the like what we used to do in the form. I'm
No,
not.
so that's why, Shubham, that's why problem what we cover here, very simple problems, and you have to extend it. You know, that the problem could be difficult. So this is example of even more difficult problem. And this is not actually, if you see these kind of things, you will get, you can get, basically. That's what I mean say. So in let us say in a heat transfer problem also you can get. In heat transfer problem, we said that the surfaces, there is no heat transfer taking place from the surface, but if there from the surface, if it is not coated, for example, and heat transfer going on from the surface, in that case this kind of equation can come into picture. Okay, so let's do it. Okay, Okay, so there may be some students who has class just after starting 11 o'clock, so they can leave if they want. Anyway, it is being recorded, and this will be available. I mean, I will share the PDF also, so you can see that. But in order to find out a weak formulation, what do you do? Very simple. You do the same stuff as we do. So 0 to LW, you multiplied by K, dA square U, dx square, right, minus lambda U and 2x square, right, is equal to dx is equal to 0, right? Okay, then once you have that, then you expand it. Yeah, the thing is you have learned the process. So 0 to L you will do, then W K d square U dx square dx, minus 0 to L, then you have W lambda U dx plus lambda times 2x square dx, right, is equal to 0. Rest is you are going to find out do the operations. Remember that here you are not going to do anything because it has W and U both together. They appear in the similar fashion, so you are not going to do anything. Here also U is not just W, so it will be just like this only. There is no other things you are going to do. Only this you have to expand, all others remains the same. So the first term is 0 to L W, and then you have a kappa, right, and d square U dx square dx. So d square U dx square dx, and you do the similar way. Yeah, kappa is a constant, so kappa will come out, but doesn't matter. So you have W kappa du over dx, and from L to 0 minus 0 to L. Yeah, and then you have kappa dw over dx du over dx dx. Yeah, is equal to, now what is given? Given is u0 is 1. That really means that at both the ends, right, both the ends, this is given. The essential boundary condition is given, so this will be W0 equal to 0 and W1 is also equal to 0. Okay, so that really means that if you put this value here, WL, that becomes 0, this also becomes 0, so the whole thing will be 0. Yeah, so is equal to simply minus 0 to L K dw over dx du over dx dx. Right? All other terms remain the same. So what you get from here is this term we have minus, so everything, now summing them up, everything becomes minus 0 to L K dw over dx du over dx dx minus 0 to L, and what do we have here is minus W lambda U. So minus lambda WU dx plus 0 to L W2x square dx is equal to, yeah, so this is what is.
So your voice is not audible.
Okay, so you have this negative, this positive, right? So that really means these both will be one side, this will be both. So what is interesting here is you can see W is here and U is here. W and U both are there. So this will also go into, both will be participating in making K. So both will together give you Ku, and this term will give you F. So this is K times U, and this will be giving you the F value. So this is the usual K, the stiffness matrix this will give you, but this term will also add to the stiffness matrix. So now your K value will be different. Hello?
But
Yes,
sir,
sir.
it will be symmetric, right? Because
It will
we
be
have
symmetric.
okay.
Yeah. It will be symmetric, but your K value, when you are going to solve this kind of problem, so let me write that side. Okay. So if you want to see how, when you solve this problem, then what K will be, K matrix and all. So that interesting, you can see this 0 to L we have, then we have kappa dw over dx, du over dx, and dx plus 0 to L. Then you have lambda, probably lambda wu, right? So then we have lambda wu dx is equal to 0 to L, and then you have w 2x squared dx. And this term will give you, finally, if you solve it, when finally you solve it, so you can do yourself, because anyway in problem it is not asking this thing, and will give you here W1 and W2. Then you will have big K, and then you will have U1 and U2. If you are using the two noded element, right? So, and this will be giving you W1, W2, and F1 and F2. When you solve it, right? And K value, you can see here, K will be have K11, K12, K12, K22, where K, I can write here, Kij will be equal to, it will have two terms, 0 to L, yeah, and you will have a kappa, and then you will have dni over dx, dnj over dx, plus this is coming from here, and here, from here also it will come, right? And what will be the value? You can relate now, 0 to L lambda ni nj dx. Got it? Because here it is derivative, so n will have derivative. Here there is no derivative, so n and ni nj will just multiply. But K term will have this automatically. So you understand, Shubham, you also understand now why the weak formulation is needed, so
Yes,
that
sir.
you know which term will go where.
Sir, actually,
Yeah.
this extra term was like I was thinking about this extra term only, like what effect it will be having, because it was not getting uh, nullified by anything. So I was thinking about this.
Yeah.
Yes,
So
sir.
you have, see, process, you have to follow the same thing. It's the same process, but you can solve a very powerful problem. Now here, this 2x square is nothing but it's kind of bx. This is bx, body force only. This is body force. So body force, automatically now you have to find out F1 and F2. So accordingly you uh, have to find out, right? So for example, N1 and N2, here you can write F1 and F2. So F1 will be equal to 0 to L, and you have N1 x multiplied by 2x squared dx, and F2 will be 0 to L N2 x 2x squared dx. So everything is done now, right? And you know that the U is equal to U1 and U2 transpose of that. So you see, we have actually solved the problem, not only the weak formulation, but you know how to solve this kind of problem. You can actually find out U1, U2 now. Yeah.
Yes, sir.
So that's why weak formulation is so important. I am glad that you asked. This kind of problems, you don't know what kind of problem are. This is just mathematical expression. Then you cannot apply physics. Then you cannot say, okay, force is like this, so we put node here and there. You cannot do like that, right? It's just a mathematics, and you can solve it. So actually, this objective of this course is that also, that one thing is that the heat transfer problem, or diffusion problem, or the elasticity problem, those we deal like mechanical engineering deals with it. But even if there's some equation is given and you are not told what kind of problem it is, still you should be able to solve. And finite element analysis was developed by more mathematician than mechanical engineers, basically. So I mean, if you see the origin also, how like this Gaussian method or Rees method, they are more mathematics rather than mechanics. Yeah.
Sir, in 3.13 question, sir, like we have this du by dx, so we'll leave it untouched, right? Because like if we'll do integration by parts, it would only shift to w.
So 3.13 you are saying?
Yes, sir.
Yeah. So find the weak form for the following a strong form. This subject to u0, u1 equal to 0. So what are you asking?
Sir, like this, we are having this du by dx term, so we'll multiply by w. So if we try to do anything, the differentiation would only move to w.
There you do not have to do anything. Yeah.
Yes, sir.
In that case, so in that case, you do not have to do anything.
And sir,
So
what
just,
about the symmetricity? Like,
still it will be like that. You know, this sometimes like it is possible that in problem 3.13, if you work, you may simplify it further somehow. You know, so that these two terms, it may be simplified also, but in case it's not being simplified, it's okay. Why I'm asking? Because what is the problem here is you have x multiplied by d square u dx square, but not it should be inside like what do we do? D over dx, right? And then inside we have e as a function of x and a as a function of a. But in this case, x is outside. So first you have to convert this in a form where the second differential is outside and there is nothing outside of that. You got it, what I'm saying?
sir, what is outside?
Just a minute. Let me save it, because this can only, there can be only maximum 20 pages. Okay, let me save it first. Okay, I have to open new page now. Just a minute. Should be lecture 16. Okay, so let me see. You are saying problem 3.13. Okay, and what it's given is x d square u over dx square plus du over dx minus x equal to 0, right? And this is, it says 0 x1. Yeah, and subject to u0 is equal to u1 equal to 0. That's what it says, right? Okay, so now we have to find out the weak formulation. Okay, what the problem is here is if you see we are used to, and we have seen that we have to get something like this you have, right? EA du over dx. Then we say dx, then we multiply w, right?
Yes, sir.
Yeah, we do like that, right? So what happens is, now in your case you have this x here. So earlier there was nothing here, right? W comes later on, right? So our equation is typically bx equal to 0. So there is no equation, there is no nothing, no expression here, right? But here you have
Sir, I think I got it. X du by dx is combining these first
yeah.
two.
Yeah.
Okay.
So how will you do? Accordingly, you will see. Let's solve the problem. No problem. Okay. So let's look at this. So you have to be careful. That's what I'm saying. In the beginning, I said you have to be careful. So let's see. So you have w, and then you have x d square u dx square plus du over dx minus x dx equal to 0. Right. So 0 to L you have. Now you have to be careful, as I said. So first we expand it always. So 0 to L. And then you have W times X. D square U dx square dx plus 0 to L W times du over dx minus 0 to L W times X dx equal to 0. Right? So this we don't have to do anything. This also we don't do anything. Yeah, so there is no point of doing anything. Yeah, so we keep it like this, and it will be symmetric. It's not like it will not be symmetric. So I mean, we will see. Maybe this term will not be there. So how do we know? So let's work out first. So let's take the first term. Okay, so first term is 0 to L, and then we have W times X d square U dx square dx. That's what we have, right? Yeah. Now remember that these things are together. Yeah. So if we work like this, then we will have this equal to nothing but W times X, right? Then du over dx, and then L to 0 minus 0 to L, and then you have du over dx, right? And then du over dx, and then we will have dw x over dx. Yeah, both should go together here, remember, otherwise it will be wrong. So here we have this term. So if you have confusion, always you can work out like this. So 0 equal to L wx, then you have d over dx, du over dx, and dx. So you can see that this is a sort of dx and dx cancels out. So we have du over dx. So this multiplied by this should be here, and then this will go here, and this will come here. Simple. Yeah, that's how you exchange, right? Okay, so this you got that, right? And equal to, now at both the points at u equal to L and 0, both places you have 1, and that tells that both W0 equal to W1, both has to be equal to 0. Yeah. And similarly, we are going to put those values. So this WL, so WL is 0 and W0 is 0. Both are 0. So this will cancel out. And finally, we have minus 0 to L du over dx. Now you can expand this. And what do you get? You get d, we can write as W, right? Or okay, so write x times dw over dx plus w. Correct?
Yes, sir.
Dx is equal to minus 0 to L du over dx times x dw over dx minus 0 to L du over dx w dx. Right? You see, you got this term now, and here you have this term.
Cancels.
Yeah, so w du over dx, and here also w du over, both cancels out, right? That's what I said. Yeah, I remember from last year that somehow they cancel out. So finally you get just this only, right? So
Yes, sir. Yes,
final,
sir. And sir, in the
yeah.
start also, if we had tried to see, like you said, we have the form where d by dx and we have inside EA du by dx. So, like the first two terms, they are itself, they can go, they are the matlab, differentiation of x du by dx. So
Yes, yes,
directly
yes.
also we could have done.
Exactly, you could have done the same thing. Yeah, you simplify first and then go ahead from there. Yes.
Yes, sir. Sir, but like how, like what I have seen in the book, they are saying that if we are having dw by dx and du by dx, then we can say k is symmetric, and if we are having w and u, then also k will remain symmetric. But what about this x, which we are getting here extra? Like we have others are not constant, or are they should be constant, or they don't matter.
You will get symmetric. You will get symmetric. Okay, so
Okay.
k will be symmetric. Yeah, k will be symmetric always. Okay.
Okay, sir.
Yeah, this is also because of like first of all, the way it is formulated always. So for all the problems, this will be like there is no difference between kij and kji. There is no difference. There may be some problem where you have certain conditions, then probably it may not be. But that problem I have not seen actually. So I don't think it will be it will not be symmetric. Yeah. Yeah, got it.
Yes, sir.
So I mean, why it has to be symmetric? First of all, you tell me. The K matrix has certain features, and what it has is you see that K, at least from mechanics point of view, you can think about, right? So you have like, as I said earlier, the forces has to balance. Yeah, so those kind of things, like in beam problem, for example, for the bar, the one elasticity problem and all, you can see from the forces. This is the symmetry. Actually, symmetricity tells you that the forces are balanced. So you can see, basically mechanically, you can see that since a stiffness matrix depicts, it tells you the forces basically, right? All the forces, sum of all the forces has to be 0. And so automatically this makes sure that it is symmetric only. So from mechanics point of view, if you see, it has to be symmetric only. Yeah. Any other question, guys? Okay, if there's no question, okay, all the best for your quiz. Okay, see you on Monday.
Thank you, sir.
Thank you, sir.